Hey guys, so in every course, every year, we always seem to run out of time studying quantum physics, which is a shame because it's probably the most interesting and most sort of cutting edge of what's happening right now. This video, we're going to look at the wave function, and the big question is really, where is the electron? Remember, we discussed the idea of the de Broglie wavelength, and we came up with a function that looked like this. We had the lambda equals h over p. Remember, and that came from this very powerful statement that combines Max Planck and Einstein's idea that the energy of the particle, or the energy of the wave, or the energy of light, can be described particularly or particulately with a particle or as a wave. And so what de Broglie came up with was that perhaps if waves, this light could behave as a wave in the sense of the frequency description, perhaps matter could act as a wave. And so he came about with this whole idea and eventually ended up with this solution, which is just moving around some variables. We're obviously plugging in, substituting in frequency times wavelength for c, and you can do the rest of the isolation of lambda. So this whole idea is kind of weird because what it says basically is, as we looked in one of the experiments, is that if I take a double slit experiment apparatus, okay, like we did in the Thomas Young experiment, which clearly defines what a wave property is in terms of interference and diffraction, we would expect to get the electrons like little, balls of paint or marbles to hit the screen and just make two spots. But instead, what they found was not that. If they allowed electrons to shoot through these two spaces, what we would get is that interference pattern that we had before, where we have a central maximum, and then we have these alternating light and dark bands. So this indicates that the electron is behaving in a very wave-like sense. Now, Erwin Schrödinger, which is the name of the guy that you see the picture of up there staring at you as you learn your physics, he came up with an idea which we now call the wave function. And this idea is very revolutionary, but it's also very debated, and it's almost infamous in a sense in its interpretation. So let's take a look at it, because that's, after all, what this video is about. Alright, so here up on the screen we have two things, and you can see there the hydrogen wave function. So it shows all these different sort of possibilities of space where the electron occupies, and you can see there there's so many different combinations of possibilities in different excited states. And so this equation is something you do not need to know for the AP exam, but that is very interesting. And if we take a look at it, it's got some very odd symbols. We've got Planck's constant, we've got the mass of the particle being described, we've got an operator there, del squared operator, that's the upside down triangle. We've also got something to describe the forces that are acting on the particle. There's an imaginary number in this function, and there you can see there's some sort of derivative of time. Now the wave function itself is trying, in a way, and this is the simplest way to describe it, it's trying to predict the location of the electron if it's acting as a wave. Because it's easy to know where a particle is, in a sense, but how can you describe where a wave is? And so we're going to go to an interpretation. We're going to look at this Greek letter psi, okay? This is uppercase psi, this Greek letter, and this is going to be described as the wave function, and it's a function of this position of the electron. So when it's graphed on a graph, we'd have its position and the amplitude of this psi. Now what this wave function actually is kind of sort of ethereal, and it's difficult to kind of pin down. But the major point is that, and the sort of major idea that has been used to interpret the wave function graphs, is to look at the amplitude of the wave that forms. You might get a wave that forms somewhat like this, all right? And what Max Born, a famous physicist who helped interpret this, he sort of described this as the probability of finding the electron. So, in a sense, sort of like the gas probabilities from thermodynamics, it's most probable to find the electron at this position right here, x sub naught. If I call that x sub naught, or maybe over here at x1, or over here at x2. I'm just putting some random letters down, actually random subscripts down. And what it is, in what we need to know is that it's a probability curve. So x sub naught, this location right here, is the location where you're most likely to find the electron based on all these other parameters, right? Based on the mass of the particle being described, this sort of divergence idea here, the del operator. We've got like what forces are acting and all these other things that are influencing the position of where the electron is and what shapes the wave of the electron. So let's look at a few different pictures. Alright, so here's a picture that is subtitled "A Wave Packet Corresponding to a Particle Located Somewhere in the Region X." So within a region of space, where are you most likely to find this electron? Perhaps that's what the wave nature of the electron is telling you. It's telling you probabilistically that it exists somewhere. And where is it going to exist in the future, and where is it going to exist in the past? And it kind of interferes with itself to predict this pattern. And so wherever the amplitude is the greatest, so right here where the amplitude is the greatest is the most likely place to find an electron. That's really all you are looking for in these kinds of questions, is one, to understand that electrons are not, we cannot measure the position of the electron and know it at all times, because it is represented, its locations are represented as locations in space. So let's take a look at some questions on the AP test. Will have you, sort of interpret these seemingly weird looking graphs, and they may give you, say, these two graphs, and they'll say, let's label a spot x sub naught, and they'll say, at which x sub naught on the left or the right are you more likely to find an electron? Well, the one with the greater amplitude. The frequency has no meaning in that regard, and so we would pick the blue one on the right-hand side and say that because it has the greater amplitude, that's where you're most likely to find the electron. So if you look at Schrödinger's equation, which is very complicated and very difficult to solve, in fact, computers solve those, we interpret it, and what we need to understand is that it is a way to interpret where an electron is at a given time based on all these factors that are affecting it and where it could be. So you can think for different molecules, you're going to have very different wave functions, right? And then within the molecular, or different atoms, you're going to have different wave functions. And then in different excited states, in different isotopes, different ionic forms, you're going to find different wave functions of where the electrons are. So it's kind of a cool, a useful way for physicists to describe the location of electrons. Now, it turned out there was a huge fight historically between Einstein and Bohr over this interpretation, and Einstein was very against the idea that the fact that we measure things influences the sort of reality of the situation. So he sort of believed, in a simple sense, that there's an absolute answer, and we just hadn't found it yet, and that it was possible to know. And Bohr was basically saying, no, the fact that you influence the measurements mean that it's really interpreted, it's a probabilistic existence, and that it depends on so many things as to what the truth really is. And so it's very philosophical, and I hope that it sparks some interest, that you might pursue reading or studying more about the electron and quantum physics.